Here we go into Cartesian trigonometry. I love that background, by the way. A lot of pi symbols mixed together. This is a big one. This is an important one. And if you've looked ahead, you're going to notice we do have some extra time for review on Monday and Tuesday before you have your trigonometry test. So make sure you watch this once, maybe watch it twice. Make sure you ask me lots of questions. You're going to get a lot of information. But this is an incredibly important lesson that sets up the next couple lessons and then obviously leads us into grade 12. Our learning goals, we're going to learn about trig ratios in coordinate geometry. So we're no longer talking about triangles necessarily. We're going to use something called the cast rule. We're going to learn about the cast rule. We're going to learn about Bowtie rule. There's going to be lots of information coming at you. Exciting stuff. So I'm going to start off with we're going to throw a bunch of things on here. Definitions, key terms, ideas. We're basically going to make a word wall, if you will, or an idea map. So we're going to start with the unit circle. And the unit circle is called the unit circle because it has a radius of 1, which is what that line going across labeled 1 is. And if it has a radius 1, we know what all those coordinates are on the x-axis and y-axis. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. You can actually get any coordinate along that unit circle using cosine and sine. So the first thing I'm going to add here, we'll use black. So any coordinate along that unit circle has coordinates x and y. So we'll make this here. You can actually express any of those coordinates with cos and sine. So we can actually write any coordinate along the unit circle as cos theta, sine theta. And if you're not sure what theta is, just a Greek symbol for angle. So to prove it to yourself, let's throw in some degrees along this circle. First of all, we know that there's 360 degrees in a circle. So I'm going to label this right here on the side of the x-axis. That's 0 degrees. Type in cos 0. You get 1. Type in sine 0. You get 0. We just got the coordinates for 1, 0 using cos and sine. Moving along, this right here would be 90 degrees. Type in cos 90. You get 0. Type in sine 90. You get 1. There's our coordinate again. Now I'm picking nice coordinates, but again, this would hold true for any of the coordinates. Any of those curved ones are going to be nasty decimals, but this holds true. Moving along here, 180 degrees. Type in cos 180. Negative 1. Perfect. Sine 180. 0. Got the y coordinate. Down here, adding another 90. That's 270. Cos 270. Type that in. You get 0. Sine 270. Negative 1. And then coming full circle, 360. Cos 360 is 1. Sine 360 is 0. We got that exact same coordinate back. So every single point along that unit circle can be written with cos and sine. Now you're going to notice that I went around in a counterclockwise direction. So from now on, when we're talking about Cartesian trigonometry with angles, no triangles, but on a coordinate grid, when you move around your circle this way, so counterclockwise, that is moving in a positive direction for theta. And again, that would be counterclockwise. The converse obviously holds true. So if I go around this way, which would be clockwise, that's traveling in a negative direction, so negative angles. So negative direction, this would be for negative versions of theta, negative angles, and that's clockwise. The next thing I want to add to this, so we're going to draw a line from the origin to there, and we're going to call that point P. And you can take from that point, and you can draw a dashed line down, and that makes a 90-degree angle. That's going to help us. And that obviously would be an angle between 90 and 180, let's say 135. So again, you always start at 0, and if you're going at a positive angle, positive direction, you're going to go counterclockwise. So I'm going to label that theta, and then I'm going to put a beta here. We're going to talk about what each one of these things are. So yes, we've said theta is the angle. Theta, though, is the angle between the initial arm, and if you're thinking, what's the initial arm? We're going to get there, and the terminal arm. In standard position. So you're going to see these terms pop up now. We're going to talk about what each one of these mean. So the initial arm, let's talk about that. The initial arm is just where you start, which for us almost always is going to be this line right here that I'm doing in purple. So that right there is the initial arm. In other words, where you start. And then you rotate that around. And if we're talking about a positive angle, counterclockwise. And you end up at the terminal arm. What's the terminal arm? Well, the terminal arm is this right here. And the terminal arm is just where you take that initial arm like the hand of a clock and you rotate it around and you end up at some point P after you've rotated it a certain number of degrees, theta. And theta is the angle between them. Now, if we go outside of between 0 and 90, we're obviously talking about obtuse angles. However, I know that there's a relationship that exists, SOHCAHTOA, Pythagorean theorem, when I use 90-degree triangles, which is why from the point P all the way, draw that dashed line down, makes a 90 degrees. And that makes a right angle triangle. And then we have this Greek symbol called beta. And really, you could use any symbol you want there. We're just going to talk about how it is in your textbook or in typical math places. Beta. And this is called the correlated acute angle. Because there's a relationship that exists between theta, the angle in between the initial arm and the terminal arm, and the correlated acute angle beta. And it's acute because it's always going to be less than 90. Now, if we take a look at that triangle, so I'm just going to pull that triangle out, pick a different color here. Where do I want to put this? Let's put it up here. So we have that diagram going on, right? And that was P. We know that a relationship exists, so if I call this beta, but it's in coordinates. So instead of calling it like A, B, and C, really any point P on the terminal arm can be written as a coordinate. Say negative 0.8 and negative 0.9, let's say. Well, those are just distances. Those are your y distance or your y coordinate, your x distance, your x coordinate, and then r for radius. And so far you've been told, SOHCAHTOA, which you can still memorize things in that manner if you want. Or there's another acronym that other teachers might use. Obviously not, again, in grade 11, but depending who you have in grade 12, you might see this. SYR, CXR, and TYX. Cirkix or ticks. So we got SOHCAHTOA, Cirkix or ticks. Those are the exact same thing. So if you ever see them again, you don't have to memorize Cirkix or ticks as long as you know SOHCAHTOA. But think about it like this. So if we talk about SOHCAHTOA, here's my angle. That would be opposite, right? That would be adjacent, and that would be hypotenuse. So sine is y over r, opposite over hypotenuse. So in this case, sine beta is y over r. Cos beta would be x over r. And tan beta would be opposite over adjacent, which would be y over x. Again, it's the exact same thing as SOHCAHTOA. Whew, okay. Hopefully your mind's not blown yet. A lot of information. You might want to pause, rewind, listen to it again. Let it try to absorb through osmosis. But we're going to do lots of examples. And again, this is setting up our foundation. And once we practice it more often, this lesson, next lesson, future lessons, it should become a little bit better. And it's really, once you get going into it, it's not too bad. Cast rule and Bowtie rule. These are going to help us. So x and y, and I'm going to call this as quadrant 1, quadrant 2, quadrant 3, quadrant 4. We're going to write the letters C-A-S-T. C-A-S-T. You always start in quadrant 4 and work your way around counterclockwise, spelling the word cast. Now, how is that going to matter to us? Well, any angle in standard position that ends up in quadrant 1 where it says A, the A stands for all. So all trig ratios are positive. If we end up in quadrant 2 with our terminal arm, only sine, so only sine theta is positive. If we end up in quadrant 3, where there's a T, if you're getting the idea, only tan theta is positive. Down where the C is, quadrant 4, only cos theta is positive. So we're going to have terminal arms that show up in those quadrants. That just helps us quickly come up with the sign of them, meaning sign of like positive or negative. So they're either all positive, only sine, and the other two are negative, only tan, the other two are negative, only cos, the other two are negative. And that is our cast rule. Bowtie. Again, we're going to make an x and a y. And you make a bow tie. The triangles that you draw in Cartesian geometry, okay, should only ever look like that, make a bow tie. So it should, and those are 90s, and those are 90s, and there's all of our related acute angles. And that angle theta is always between the terminal arm and the x-axis. That related acute angle. So always between the terminal arm and the x-axis. So you should never ever draw a triangle that looks like this, or like this, or like this. That's an hourglass. This isn't the hourglass rule. This is the bow tie rule. So we're gonna, if we do this, this is very, very sad. We don't want to do that ever. So don't do. Bow tie rule, cast rule, we're going to use those to help us in addition to all the information that we just came up with. On to an example. So example 1, the point 512 is on the terminal arm of an angle in standard position. Find the ratios for sine theta, cos theta, tan theta, then find what the angle is to 1 decimal place. Step number 1. This is Cartesian trigonometry, draw an x and y axis. The coordinate 512, that is in quadrant 1. So terminal arm, some point P, we'll call it capital P, 512. Based off of the bow tie rule, we are going to make a 90-degree triangle. There it is. Saying that the terminal arm is in standard position, that just means that your initial arm is there. And theta is always between the terminal arm and the x-axis, the initial arm. So how do we figure this out? Well, if x is 5, that tells us that this distance is 5. Y is 12, so that distance is 12. The only thing you are missing is you're missing your radius. You're missing your hypotenuse. How do you get that? That's a 90-degree triangle. Pythagorean theorem. A squared plus b squared equals c squared. Or in this case, 5 squared plus 12 squared equals r squared. 5 squared is 25, plus 12 squared is 144, that's 169. Square root, not plus or minus because negative 13 has no meaning. We can't have a negative distance. 13 is there. So there we go. That's a really good first start. Now we've got to find sine theta, cos theta, and tan theta. All right, let's start with sine theta. Well, you could remember SOHCAHTOA, opposite over hypotenuse, or circx or tx, y over r. Either way, 12 over 13. Cos theta. Remember it as adjacent over hypotenuse, or kixer, x over r, 5 over 13. And tan theta, opposite over adjacent, y over x, 12 over 5. So far, not too bad. Now, we want to know, it also asks us to find the angle to 1 decimal place. So theta equals sine inverse 12 over 13. Using your calculator, sine inverse of 12 divided by 13, we get 67.4 degrees. And that makes sense, 67.4 degrees, that's definitely quadrant 1. Do you have to use sine? No, you could have used cos. So just for fun. I mean, you could stop there, but let's see what happens when we do this. Cos inverse of, oops, not 12 over 13, 5 over 13. Cos inverse of 5 divided by 13, 67.4 degrees. Perfect. Let's see what happens when we try tan. Oh, I did it again. You can see I'm making similar mistakes that you guys might make, so make sure you learn from my mistakes. So tan inverse of 12 over 5. Lo and behold, 67.4 degrees. You can use any of those. You don't have to use all three, okay? They were all the same angle, which they should have been, because this was in the positive quadrant and they are all positive there. This is not going to be the case in any other quadrant, unfortunately. So we're going to do some examples to talk about that, but for now, simple example, everything's in quadrant 1, they're all positive, those are all the exact same degree, theta 67.4. And again, you can pick any of those. Example 2. If sine theta equals negative 3 over 7 and is in quadrant 3, find the exact values of the other two primary trig ratios. So this is kind of like working backwards. Cartesian trig, draw an x and y axis to start always first. And it's always a good idea too to actually write the letters cast. So if I didn't tell you this was in quadrant 3, sine is actually negative down at the bottom in two different quadrants, which means there could be two possible answers or two sets of answers. But I let you off the hook here a little bit easier. I told you it's in quadrant 3. So we're going to draw our terminal arm down here. Bowtie rule, that's how my triangle has to be. And again, theta is your angle from the initial arm to the terminal arm. And sometimes if it doesn't say it's in standard position, then sometimes you can just label this as the related acute angle as well. And if you can call it something, you can call it beta if you want, or theta 1, theta 2, x, y, whatever. This doesn't say standard position, so I might even just erase that to avoid confusion. Okay, so we're there. And it makes sense because it's in the t quadrant when only tan is negative, so, or only tan is positive, I should say. And we got negative 3 over 7. Now remember, sine is opposite over hypotenuse, or y over r. So this is 3 and this is 7. If I want to find the exact value, so we already know sine theta equals negative 3 over 7. And if you're wondering why I didn't label that negative 3, distances are always positive, but it would have a coordinate, y coordinate of negative 3. But that's taken into account by our cast rule. That's kind of where the cast rule comes from. So watch out for the negatives. I would to be safe, stick to positive values for distances, and then use the cast rule to come up with whether it's positive or negative. So we are currently missing my x distance. That's a 90-degree triangle, Pythagorean theorem. This time you were given the hypotenuse. So instead of it being a squared plus b squared, it's going to be 7 squared minus 3 squared equals x squared. 49 minus 9 is 40. How do I get rid of that? Square root both sides. And we learned that root 40 can be broken down into root 40 times root 10 to root 10 equals x. We don't want decimals. We want to keep things as exact values, especially if the question says exact values. If it's at approximate values, that's when you would round. So this is 2 root 10 now. Okay, so now we're ready for cos theta, which is adjacent over hypotenuse, or x over r, 2 root 10 over 7. Based off the cast rule, that triangle's in the t quadrant, only tan is positive, so that's negative. Tan theta is opposite over adjacent, or y over r, so 3 over 2 root 10. It's in the t quadrant, so we know it's positive for tan. But we've got a problem now. I got radicals in the denominator, and I don't ever want radicals in the denominator. How do I clear them? Well, you got to go back to unit 1. You multiply by root 10 over root 10. So that's 3 root 10 over 2 times 10, right? 3 root 10 over 20. Well, I have your attention on the radical information. As was mentioned in Unit 1, I don't know what kind of calculator you have. I don't know what you're typing into Google. I have to see your work. Even if I don't do it in the lesson because I know what I'm doing and I'm explaining it to you, for your test solutions, and a handful of you lost marks because of this, I need to see every step that you do so you can prove to me that you know what you're doing when you're simplifying radicals. If you happen to look up the answer or you have a fancy calculator, that's just confirming your final result. But if you don't show me how you get these, I cannot give you full marks. So I just want to drive that point home one more time. Our next example, the point -4, -5 is on the terminal arm of an angle in standard position. Find the ratios for sine theta, cos theta, tan theta. Then find what the angle, the positive angle, is to 1 decimal place. Okay. Draw an x and y axis. After we've put our x and y axis, maybe it's a good idea to write cast. -4, -5. Where is that? -4, -5. Well, that's quadrant 3, bottom left corner. So there's point P, -4, -5. Bowtie rule, there's our triangle. Now our angle, theta, in standard position goes from the initial arm all the way around to the terminal arm. So that's theta, that's what we're looking for. And that angle equals the related acute angle. So we'll call that beta here. For now, let's label our sides. So that's 4, that's 5. I'm missing r, so I'm going to have to do Pythagorean theorem. 5 squared plus 4 squared equals r squared. 25 plus 16 is 41. Square root both sides. Root 41 equals r. And root 41 does not break up very nicely, unfortunately. So, sine theta equals opposite over adjacent, or y over r. So this was root 41. So that would be 5 over 41, root 41 I should say. And since that is in the tan quadrant, sine is negative, and then we got to get rid of that root 41. I know it's kind of annoying to do, but we have to for math format. And that's what we end up with for sine theta. Cos theta. Adjacent over hypotenuse, or x over r, 4 over root 41. Only tan's positive, so that's negative. Got rid of that root 41. We end up with that. And then tan theta, y over x, or opposite over adjacent, 5 over 4. Tan is positive, and that's positive. Beautiful. Okay, now we need to find what the angle is to 1 decimal place. We only want the positive version. So we've done this once before with everything in the positive quadrant, and we could have picked any one of them. Let's see what happens. I'm going to use a different color here. Let's see what happens when we start at the top here. So we know theta equals sine inverse of negative 50, oops, not negative 51. Negative 5 root 41 over 41. So everyone type that in. Sine inverse, negative 5 root 41 divided by 41, close bracket. And I get negative 51.3. Before we move on to cos and tan, let's talk about that. The first thing everyone has to realize is that your calculator is lazy, kind of. And remember, for all of these ratios, so based off the cast rule, because there's an all quadrant, there are 2 possible solutions for any of these answers. So if we're talking about sine being negative, right, we have a negative 5 root 41 over 41. How does your calculator know that you want the one in quadrant 3 or quadrant 1? Because sine's also negative in quadrant 4, sorry, not quadrant 1. Your calculator, how do they know? They don't. So what your calculator does is it picks the closest answer that it could come up with to the x-axis. So the closest answer from basically 0. So remember, if we go around this way, that's positive. Your calculator knows that, so I'm doing this in black, your calculator knows that sine is negative here and sine is negative here. If your calculator wasn't lazy, it would be able to give you the one that goes all the way around to there. But your calculator's lazy. It doesn't, and it also doesn't know if that's the one you want. So instead, it takes the shortest distance, which again doesn't know that your triangle isn't down here. So it goes in the negative direction to give you that. That is actually useful to us because that gives you the related acute angle. Regardless of whether it's negative or positive, we know that that little angle in there is supposed to be 51.3. And if you remember from the Bowtie rule, so I'll redraw it up here, all of those little angles are all the same. So if that's 51.3, this is also 51.3. We'll come back to that. Let's try cos. Theta equals cos inverse negative 4 root 41 over 41. Let's see what happens. Cos inverse negative 4 root 41 divided by 41, close bracket. I get 128.7 degrees. So again, your calculator knows, I'm kind of color coding this, your calculator knows that cos is negative, right, because this is negative. Your calculator knows that cos is negative here and here. Again, it doesn't know where your triangle is. So it could go all the way here, or it could go all the way to here, because that's the other place where cos is negative. Based off of our diagram, the shortest distance would be 128.7. That doesn't help us any. We know it's not the case. We'll come back to that. Let's try tan. Theta equals tan inverse 5 over 4. So using our calculators, tan inverse 5 divided by 4. I got 51.3. Let's talk about that. Tan is positive. Your calculator knows that tan is positive here and tan is positive here. It doesn't know where your triangle is, and it is lazy. So it could go all the way around like that, or since it doesn't know, it might think your triangle is there. Tan's positive there, that's the shortest distance, that's also 51.3. That backs up our Bowtie rule, all those angles are the same. So we'll come back to that. All right, so let's come up with what the actual final answer is. And I know this is confusing and it's going to take some time and practice to get this through. So just bear with me. So I am looking for theta, which I know I got a lot of arrows in there, a lot of colors. Theta is all the way to here. That was our initial one. So I'm going to make that nice and bold. I know the related acute angle. I calculated it from this, and this backed it up. It doesn't matter which one you pick. Again, we don't care about the negative, that's just direction. We care about the absolute value, which is just the positive version. I know this line right here is 180. So to get all the way around, I would do 180 plus 51.3. So theta equals 180 plus 51.3. Well, what's 180 plus 51.3? 231.3, and there's your angle. In standard position. Now I said I would come back to the cos. And again, you can use any of these. It's just totally, how do you wrap your mind around this? I got 128.7 for cos. If you use that and did, right, so 128 gets you to that first purple one right here. If you did 180 minus that, 128.7, what do you think you get? Let's try. 180 minus 128.7. 51.3. You can see all these angles are related. So what you just calculated right there was the related acute angle. And once you had that, you could have used that to realize that's my related acute angle. I could do 180 plus that to get those angles. Okay, let's all take a moment here, relax. Pop those huge question marks you have over your head. I've explained to you how you can use all three. I certainly don't expect that just listening to it and watching it for the first time, you have a full understanding of what's happening. You do not ever have to use all three of those. You can use any of those to get a way to get your final answer, which I just showed you how. You have to practice. You absolutely have to ask me as many questions as you need to ensure your success and to ensure that you grasp this. Again, not only is it important for what's coming ahead, it's important for grade 12. Example number 4. The point P, negative 5, 6 is on the terminal arm. Determine the primary trig ratios of A. Label the correlated acute angle B. What are the measures of A and B? Okay. X and Y axis to start. Cast. Perfect. Negative 5, 6. That's over here. So there's the point P. Negative 5, 6. Bowtie rule. Triangle goes down.
Here's a summary from Investopedia.
Let's label our dimensions of our triangle. So the x coordinate, negative 5, we just care about positive distance. Y coordinate, 6. 5 squared plus 6 squared equals r squared, right? Pythagorean theorem. 25 plus 36 is 61. Take the root of both sides. Unfortunately, that doesn't break up very nicely. So that's root 61. Okay. Angle A is in standard position. That means it goes from 0 to our terminal arm. So there's A. There's B. We want the primary trig ratios of A, which we know they match B. So sine A equals opposite over hypotenuse. Sine A equals opposite over hypotenuse, y over r, 6 over root 61. Since that's in the S quadrant, sine's positive. I'm going to cut to the chase here. On your test, you would show you multiply by root 61 of root 61. Hopefully we kind of realize that's what we're going to end up with. Cos A, x over r, adjacent over hypotenuse. 5 over root 61, negative, because it's in the S quadrant. And that equals negative 5 root 61 over 61. Tan A, y over x, opposite over adjacent, 6 over 5. Negative since it's in the S quadrant, and we don't have to do anything with that. Okay, so there's A done. And we already labeled the related acute angle. What are the measures of A and B? Okay, so this is where you have some choice. I'm not going to go through all three of these. I'm going to go through, I'll do the first one, sine A. We'll see what happens, and we'll adjust accordingly. If you don't like what I get for sine A, you could do it for cos A and adjust. You could do it for tan A and adjust. It totally is how you understand this. You do not have to do it for every single one. So A equals sine inverse 6 root 61 over 61. Taking out our calculators, let's try that. Second function or shift, 6 root 61 divided by 61. I get 50.2 degrees. That does not mean that A is 50.2. So again, this is where we're going to adjust. Your calculator knows, since we did sine and since it was positive, your calculator knows sine's positive there and it knows sine's positive there. It does not know which one you want, which that triangle I just drew could be the other one. So instead of going all the way to B, again, your calculator's lazy and also doesn't know which one you want. It gives you the closest one to 0 to the x-axis, which is that one. Since it's positive, you know you're going in a counterclockwise direction. So it gave you that angle right there. That is still useful. This is how we're going to adjust based off the Bowtie rule. So I'll do that again up here. All these little angles, they're all the same. So if that's 50.2 and that's the acute angle, we've just found B. B is 50.2. And if our triangle was in quadrant 3 and quadrant 4, those all acute angles would all be 50.2. So we just calculated, actually, even though it was labeled as A, we calculated B 50.2 degrees. How would you get A? Remember, A goes all the way around. Well, we know this is 180. If I was to do 180 minus 50.2, what's left over would be this, right? So this is our angle in standard position. That's our A. If I do 180 minus 50.2, that will give me my angle. 180 minus 50.2, 129.8 degrees. If you chose to use cos A, you would have to do some adjusting, and if you chose to use tan A, you would have to do some adjusting, kind of like we did, some thinking. For the record, in that little bow tie diagram I made, any angle that's in quadrant 2 is always going to be 180 minus. Any angle that's in quadrant 3 is going to be 180 plus. And then if it's in quadrant 4, that's going to always be 360 minus. And quadrant 1, they're all positive. They'll be acute. It'll be whatever the angle happens to be. So we could just label this x and 180 minus x, 180 plus x, 360 minus x, and so on and so forth. Okay, maybe, hopefully, we feel even just like a smidge, like a fingernail width better about this. Maybe we don't, and that's okay if you don't. Our last example, write an equivalent correlated angle to each of the following and an equivalent trig ratio. Start out with x and y. Cast. Sine 100. You kind of have to know where that is, roughly, of course. If that's 90 and that's 180, obviously 100's over here. Bow tie rule. I know that is 100. Where it is, sine is positive, right? So where else is sine positive? Sine is also positive, so I'll use a different color here. Sine is also positive over here. I need that related acute angle. Well, how do I get that? 180 minus 100 equals 80 degrees. And if that's 80, that's 80. So that means that sine 100 equals sine 80. So our equivalent correlated angle is 80. Our equivalent trig ratio is sine 80. Prove it to yourself. You can always double check your answers to these things. Type in right now, sine 100. I get 0.9848, blah, blah, blah. Type in sine 80. Whoa, same number. They're equal. We did it. Now you can't start with these and work your way backwards. So I do have to see the work, that diagram, with a little bit of subtracting that we did. Let's try it again. X and Y. Cast 100 is over here somewhere. Bowtie rule, there's my triangle. That's 100. Now it's cos. That's in the S quadrant, which means cos is negative. Where else is cos negative? Well, cos is negative in the T quadrant, so this would be my other option. I got to figure out my correlated acute angle. So just like before, 180 minus 100 equals 80. And if that's 80, that's 80. So cos 100 equals, now remember, cos is negative in quadrant 3. So my other angle is the one that goes all the way to there. How do I get that? 180 plus 80 equals 260. So cos 100 equals cos 260. Let's double check our answer. Cos 100, negative 0.17, blah, blah, blah. Cos 260. Whoa, same thing. Awesome. Let's try it again. Cast tan 200. Where's 200? Well, if that's 180, 200 is down here. So there's 200 degrees. That is in the tan positive quadrant. So where else is tan positive? Tan is also positive in quadrant 1, right? So I got to figure out what this is, which means I need my correlated acute angle. How do I figure it out? Well, if my first one's down here and I subtract 180, I get what's left over, 20. If that's 20, that's 20, which means tan 200 equals tan 20. Let's check it out. Tan 200, 0.3639, blah, blah, blah. Tan 20. Oh, we didn't, kidding. We got the same thing. Hopefully you're as excited as I. I actually like this, both sarcastically, but seriously, I actually really like coordinate trigonometry. And maybe you will learn to love it as well, or maybe you won't. 210, where's that? Well, that's 180. 210 is somewhere down here. Okay, so there's 210. Based off the cast rule, that is in the cos negative quadrant, right? Only tan is positive. Where else is cos negative? Well, cos is also negative here. So that would be that angle right there. I gotta figure out my correlated acute angle. How do I do that? Well, I'll take the first one, 210 minus 180 equals 30. So that's 30. And if that's 30, that's 30. So how do I get this angle here? 180 minus 30 equals 150. So therefore, cos 210 equals cos 150. Cos 210, cos 150, exact same answer. Hopefully now seeing it a fifth time, we have just a smidge more comfort with it. Again, if you don't, that's okay. You are not alone. This is one of the more, aside from Unit 1, this is probably one of the more difficult, not full units, because the other trigonometry stuff is not hard, it's grade 10. But this little half unit, the second half of trig, is probably one of the hardest things that you're going to do in this course. But you can get better at it with practice and asking me as many questions as you possibly can. There is your seat work plus a test review. And remember, we are together on Monday and Tuesday of next week. So you have some time to practice, maybe work on some things over the weekend, take a little bit slower, work on things on Monday, maybe Tuesday morning before you start your test on Tuesday afternoon. That's it. Thanks for listening.